We'll be starting our respiratory physiology lab with a look at the important terms as usual. So the first part here is lung volumes and capacities. So that would be as recorded with a spirometer. You would record the various volumes and then you can add up the different capacities. So a volume is a single measurement versus a capacity is a compound of more than one volume. And the volumes and capacities here in question are listed right here, most important ones. The tidal volume is abbreviated as the TV. The inspiratory reserve volume is the IRV. The expiratory reserve volume would be the ERV. The residual volume is the RV. The anatomical dead space is usually abbreviated as ADS. The vital capacity, very important measurement, is VC, and the total lung capacity is the TLC, right there. So now, how do you get these measurements? Basically, you are breathing in and out of a tube, and the volumes that you're breathing in and out of this tube will be measured. So if we are just let me set this up here. So let's say you have here on the x-axis, of course it's always the timeline, and then here on the y-axis we have the volume. And as you normally breathe in and out of your lungs, that is known as a tidal volume. So just picture the ocean tides coming in and going out. And so it's sort of this normal rolling of your tidal breath in and out of your lungs. And it's not all the way down in the bottom. Of course, you don't collapse your lungs to do a tidal breath, and you don't go all the way up to the top, the maximum capacity of your lungs, but you are rather breathing in and out somewhere in the middle here. So we're going down. Nice normal tidal breath like this. So the height of one of these waves, that would be the tidal volume. So I'll put this right here. So the height of one of these tidal breaths, that's the tidal volume, and it should be about 500 milliliters. Sort of the average number for a normal tidal breath is about 500 milliliters. Now, let's say if you were to decide that you wanted to go above and beyond a tidal breath out, that means you were trying to push everything that's in your lungs out. You could certainly do that. You could definitely do better than just a tidal breath out. You couldn't go below that. So you can go like this and say, okay, I was able to breathe out some more. And then you go back into tidal breathing. So now from here, from the tidal breath out to the bottom of this whatever else you were able to exhale, that's the expiratory reserve volume. Okay, so I labeled this right here. So your expiratory reserve volume is whatever you can exhale above and beyond a normal tidal breath exhale. And it should be anywhere between 0.7 to about 1 liter. Now, there is a volume of air that you cannot exhale. Just to keep your lungs inflated, you have to have some air in there, and that is the residual volume. And while we can't really measure that, because if you were to measure it, you would have to collapse your lungs, and that's something you really don't want to do. So we're just going to estimate it at approximately 1 liter and just work with that number. That number is fine. So 1 liter, that's our estimation for the residual volume. And now we just exhaled as most as we could. We weren't able to get the residual volume out, but that's normal. And so now we're going to take a normal breath back in, and here's our tidal breath. And then here goes our tidal breathing. And when you're at the top of a tidal breath, above and beyond, at the top of a tidal breath, you can certainly increase your breathing some more, and you get some more air into your lungs. And if you try to get the maximum amount of air into your lungs and then exhale whatever is in your lungs as fast as you can, that's when you end up measuring the vital capacity. So the vital capacity is compounded of a tidal volume, one of these, plus the inspiratory reserve plus the expiratory reserve. So you're compounding 3 numbers here, and that is your vital capacity. Now, the vital capacity depends on your height. It also depends a little bit on your age and your gender. We'll calculate an estimated vital capacity in a little bit, but for now, so make sure that you understand the vital capacity. It is a capacity. That means it's composed of more than one volume. It's composed of the inspiratory and expiratory reserve and the tidal volume. And then here, next one here on our list would be the total lung capacity, and that is the vital capacity plus the residual volume. That gives you the total lung capacity from top, the maximum inhalation that you can achieve, all the way down to the bottom to the zero volume. So basically you're adding 1 liter to the vital capacity. Now, the lab would have been to measure these different volumes and capacities for ourselves. It doesn't always work the best, but hopefully you understand it in theory at least. And so make sure that for quiz purposes and everything, you just really need to know the different volumes and capacities, and I'm going to go over it in a minute again. But let's take care of the remaining terms here. Next thing is obstructive versus restrictive lung disease. Obstructive lung disease means that there's something obstructing the flow of air in and out of your lungs. A good example would be asthma. There you have inflammatory processes going on in the lungs, and sometimes people have allergic reactions, or it's just some inflammation in the lungs, in the airways. And so that will narrow the airways. It will obstruct the flow in and out of the lungs, the flow of air, that is. And so therefore, it will take people longer to exhale mostly. And when you're exercising, asthmatics will tell you about this. When you're exercising, you want to breathe more often and more heavily. Then sometimes people start to panic and they have an asthma attack because it takes them longer to breathe out. And so by the time they really breathe out, they wanted to have breathed in already, and they start to panic because they feel like I can't breathe, just because they haven't exhaled yet, and you can't add more air to a lung that's already overflowing with air. So what happens with obstructive lung disease is that you can measure this, and it will be a vital capacity that's normal, but it will take longer to get rid of that vital capacity volume. So here in green is what you might see for obstructive lung disease, that you have somebody with a normal vital capacity, but it will take them longer to breathe out that vital capacity breath. So normal would be following the purple line, and obstructive lung disease means it takes you longer to breathe out a vital capacity breath. And that is usually measured as the forced expiratory volume. And it's basically the FEV1. That means the forced expiratory volume after 1 second. It's usually a good measure for obstructive lung disease because it will take the person longer to breathe out. So you can see here, let's say this is 1 second, then you can see a normal person is almost done with their vital capacity breath versus somebody with obstructive disease has only breathed out from the top here to where the dotted line is now, that kind of volume. So obstructive lung disease, again, is characterized by obstruction to the airways that makes it take longer for you to breathe out a vital capacity or any breath, basically. Now, restrictive lung disease in sort of this orange color, that means that you've lost part of your lung tissue and it's no longer available for gas exchange. So that means you might have a fibrotic disease. There could be tar in your lungs from smoking, or coal dust if you're a coal miner. Also cancer will cause restrictive lung disease. That means now your vital capacity is reduced. You don't get up to the top here. You have a reduced vital capacity, and while it takes you the same time to breathe out a vital capacity, but your vital capacity is definitely smaller. So that's restrictive lung disease. Maximal voluntary ventilation, the MVV, that's a measure of how much air can you get in and out of your lungs at maximum rate and depth if you really tried hard. So maximal voluntary ventilation is a measure for how much volume of air can you exchange in a given time increment. Most of the time you have a person only do this for about 10 seconds and then multiply times 6, or have them do it for 15 seconds max. and then multiply times 4 to get the per minute rate, simply because if you're hyperventilating at that kind of rate, you're going to be dizzy pretty quickly. Now, the next terms here are pulmonary versus alveolar ventilation. Pulmonary ventilation is the exchange of air through the lungs, and versus alveolar ventilation means it's only taking into consideration the amount of air that actually hits the alveoli, which meaning it participates in gas exchange. So in other words, the pulmonary ventilation counts a volume of air that's stuck in your trachea and your main bronchial tree, stuff that never participates in gas exchange, but well, it entered your airways, and so it counts for pulmonary ventilation. But alveolar ventilation only looks at what actually hit your alveoli. So there are two formulas that you need to know in order to calculate pulmonary versus alveolar ventilation. So the vent pulm, let's call it this way, pulmonary ventilation is equal to the respiratory rate, so the breath per minute, times your tidal volume. And so for an example, let's say you're taking 12 breaths per minute, breath ppms, 12 ppms, and your tidal volume is 0.5 liters. Well, then your pulmonary ventilation is 6 liters per minute. It's always per minute. Now the alveolar ventilation, so that would be vent of, and that is also the respiratory rate, so that doesn't change, but you're correcting the tidal volume for the amount of air that's stuck in your trachea and the main bronchial tree and does not participate in gas exchange. So that would be tidal volume minus the anatomical dead space, the ADS, I'm sorry. So here, so the anatomical dead space, it sounds kind of bad because it's dead, nobody likes that, but it is dead to gas exchange, let's put it this way. So the anatomical dead space, the volume of air that's stuck in your trachea and the main bronchial tree, needs to be subtracted from a normal tidal volume to get the alveolar ventilation. And so let's put numbers here, 12 breaths per minute times the anatomical dead space is roughly 1/3 of your tidal volume, so let's put 0.5 minus 0.15, so that leaves us with, so 12 times 0.35, and that's equal to 4.2 liters per minute. Now, the alveolar ventilation is always smaller than the pulmonary ventilation because we are correcting for this anatomical dead space. Be sure that you know these calculations because you will be asked about these on the next quiz. A couple short things here. External ventilation, that is gas exchange in your lungs, and internal ventilation will be the gas exchange in your tissues. Cellular respiration, we already covered that a long time ago. We were actually still having class on site, and your cells want to do aerobic respiration simply because it is much more efficient than anaerobic respiration. It yields a lot more ATP, which your cells need a lot of ATP. The anaerobic threshold is when you are no longer able to provide enough oxygen to the tissues that need it, and they are forced into glycolysis, and then you have this anaerobic threshold. Also, if you're spending more oxygen than you actually have and are able to deliver, then you are running into an oxygen debt that you have to pay. So that's why you're going to be still breathing heavily after you stop exercising, at least for some time. Now, eupnea is the term that we use for normal breathing. Apnea is used for the absence of breathing. You may have heard of somebody having sleep apnea. That means they stop breathing, at least for some time while they're sleeping. Dyspnea is kind of a generic term for abnormal breathing. And then here we have a couple more terms. Hyperventilation or hyperpnea means abnormally fast breathing. And you can do this by rate or by volume. Now, either way, if you are breathing too much, you're getting rid of too much CO2, and that will cause you to run into hypocapnia, not enough CO2, decreased CO2 levels. And that leads to something known as respiratory alkalosis, and I'll show you that in a minute. Now, hypoventilation is the opposite. That means you're not breathing enough, and that means you're keeping your CO2 in. That means it leads to a hypercapnia, which is increased CO2, and that leads to respiratory acidosis.